All right, we're going to go ahead and get started. Welcome, everyone. My name is Chase Wordsmith. I'm an application engineer at Zoller Company. We appreciate you joining us for our Pump Engineering Terms 101 webinar. I began my career at Zoller in December of 2022. I graduated from the University of Louisville with a Bachelor of Science in Mechanical Engineering and am an engineer in training, currently gaining experience for my professional engineer license. I currently hold the role of application engineer on the quotations team, assisting with the sizing and selection of equipment for pump stations, low pressure sewer systems, on-site treatment systems, and any other specialty application that you may come across in the field. So now that you know a little bit more about me and my background, let's go ahead and get started. So today we're going to be covering Pump Engineering Terms 101. Now, since this is a 101 course, we're not going to go too deep into any one subject, and we're also not going to do a lot of the math behind some of these subjects that we're going to talk about today. So with that, let's get started. So let's talk about automatic versus non-automatic pumps. An automatic pump is like what you see on the screen here. It comes with a factory preset switch. It's that little buoy on the side of that pump right there. The main advantage of this pump is that they are very fast and easy to install. There's no external control that is required to operate the pump. You simply drop it in, plug it in, and your pump is ready to go. This is great for small, simplex sump and sewage applications like sump pits, flood pumps, and truck docks. Now, on the other side, we have non-automatic pumps, and these look like what you see on the screen here. There's no integral switch built into the pump. This allows for the installation of these pumps into a wider range of applications. You have a lot more control over when that pump is going to turn on and off in your system. This is great for septic systems where if you are putting a pump into a septic tank, you want to make sure that pump stays submerged at all times, since there are corrosive gases inside of that septic tank that will eat away at that pump. So keeping that pump submerged limits the opportunity for those gases to damage said pump. You also need a non-automatic pump for time dosing applications where that pump is going to be turning off after a certain period of time rather than whenever a float switch goes up. You can use these pumps in simplex, duplex, or even more pumps in an application than just 2 or 3 or 4. And lastly, as I've already mentioned, these pumps will require some kind of external start component like a control panel and external float switches as well. So now let's get into efficiency. Since a lot of this course is going to cover efficiency related things, let's talk about this first. So let's talk about pump efficiency, or rather system efficiency. So every mechanical device has power losses from input to output of that device. And efficiency is the ratio between that output and input power. So first off, we have brake horsepower. That is that input horsepower from the motor. That's typically what that motor is going to be rated for. So if you see a motor rating on a technical data sheet, that's typically the brake horsepower of that pump. Whereas you have work or water horsepower, which is that output horsepower of the pump to the fluid that pump is pumping. Now, one thing to note is that is always going to be less than your brake horsepower. The reason for that is that there is always going to be some frictional losses between that motor and the water that pump is moving through the system. One thing to note is that all pumps typically have a best efficiency point, and that's where that pump is going to be the most stable, which means you're going to have the least amount of frictional losses when that pump is operating. That's typically found near the center of that pump performance curve, and I'll show you that here in just a second. One thing to note is that if you downsize the motor in a pump, or rather upsize the impeller, that can improve the efficiency of that pump. You can typically do this with our heavy duty models where you get to select the motor with the impeller, but this can only really be done with 3-phase pumps only. Okay, so I mentioned before that your most efficient location is going to be to the center of that pump curve. So let's say you were operating to the left of the centermost point. That's going to lead to less efficient operation, which is going to also lead to wasted energy. I like to equate this to hiking up a mountain with a heavy pack on your back. It's you're wasting a lot of energy and you're not making a whole lot of progress. Whereas if you're operating on the far right end of the curve, that's where your pump is going to draw higher amps, which means that that pump's going to run hotter and shorten the lifespan of that pump. It's very similar to running at a dead sprint. It's not something that you can maintain for a long period of time, although you are making a lot of progress in a short period of time. But again, that doesn't equate to longevity. Then we have the best efficiency range. Like I mentioned before, it's near the center of that curve. That's going to be similar to jogging. It's something you do in marathons. You can maintain jogging for a long period of time. So that is going to be equivalent to running a pump near the center of that curve. You're going to be the most efficient and have the longest life out of that pump. So now let's talk about hydraulic efficiency, which is a subset of full system efficiency. So hydraulic efficiency is the ratio between the input power to the impeller and the output power to the fluid. So this is really just a measure of that efficiency between that impeller and that water. This typically just focuses on the losses in the hydraulic system only, so losses with the pump casing design, but mainly with that impeller size and type. And this is going to matter here in just a second. One thing to note is that your hydraulic efficiency is always going to be higher than your system efficiency, and that's just because hydraulic efficiency isn't taking into account the frictional losses between the impeller and the motor. One thing to note is that hydraulic efficiency is not very impactful when you're looking at very small fractional horsepower residential pumps. When you start to get into 5 horsepower and up, that's when hydraulic efficiency can have a major effect on that total efficiency. But when you're looking at small residential pumps, hydraulic efficiency is really not going to have that much of an effect on that pump's total efficiency. So now let's talk impeller styles. So before we get into each type of impeller, one thing to keep in mind is that the more contact an impeller has with the water inside of that pump, the more efficient that impeller is going to be. Now, on the other hand, the more contact you have with that water, the less solids passing capacity that pump is going to have in that application. So first off, we have vortex or recessed impellers. These have the lowest hydraulic efficiency out of all the other impellers. However, because they don't make a whole lot of contact with that water, and because the flow path is typically through a vortex that this impeller style is creating, you have the highest solids passing capacity out of all other impeller styles. Now, moving down the list, our multi-vane close running impeller is very similar to a vortex impeller. However, they tend to be a little bit more efficient than that vortex impeller. The reason for that is because these are used in our centrifugal grinders, and these are typically mounted to where there's very little space between the inlet of that pump and the bottom of that pump housing and that impeller. So the flow path is instead through the vanes of that impeller rather than below in a vortex. So because of that, that allows for higher efficiency. Next, we have semi-open impellers, and these take up a little bit more space than a vortex impeller. Because of this, they have a higher hydraulic efficiency than the vortex impeller. However, on the other hand, They have a fairly high solids passing capacity, but not as much as you would with an enclosed impeller. This is sort of an impeller that fits between a vortex and an enclosed impeller, and are typically a mix between the two when it comes to hydraulic efficiency and solids passing capacity. Then lastly, we have the enclosed impeller. These impellers have the highest hydraulic efficiency out of all the other impellers, and that's because you have the most contact with said water. Typically, that inlet of the impeller that you see there on the image on your screen is very close to the inlet of that pump. So all of that water and sewage is going to be going inside of this impeller and passing through the impeller. Because of this, these tend to have the lowest solids passing capacity out of all other impellers. So now let's take a look at some cutaways of pumps with these various impeller styles. So on the left here, we have a semi-open impeller, although an enclosed impeller is going to look very similar inside of a pump. So right there, you can see that that impeller is taking up a whole lot of space inside of that pump. And pretty much all of that water and that sewage that's going to be coming inside of that pump is going to have to pass through that impeller. Whereas on the other hand, we have our recessed and vortex impellers, where you can see that there's a whole lot more space between the inlet of that pump and the impeller itself, which means that that is giving you more solids passing capacity. So now let's talk about grinder pumps and their impeller styles. So there's really two different types of grinder pumps that are out there. There are progressing cavity pumps, which are a type of a positive displacement pump. And then you have centrifugal grinders, which is very similar to really any other centrifugal type pump. So with a progressing cavity pump, you have a rotor and stator design, which is shown in this cutaway here. And here I have a good image of the actual rotor and stator that's found inside of our pumps, and our progressing cavity pumps rather. So that rotor is that top part that's going to be attached to the shaft of that pump, is going to rotate with that motor. And then you have the stator, which is going to be attached to the bottom of that pump. And then that rotor is going to be seated inside of that stator. So as that rotor rotates, it creates these small pockets that push the water and sewage through the stator and then eventually out of that pump. The great thing about progressing cavity pumps is they output a whole lot of pressure. Now, because of the rotor and stator design, they can't pass a whole lot of fluid very quickly. So their flow rates tend to be much lower than that of a centrifugal grinder. Now, looking at a centrifugal grinder, you can clearly see that close running impeller. You can see that it's very close to the bottom of that pump housing, and because of that, all of that sewage is going to pass through that impeller and then out of the pump, which allows for a little bit higher efficiency than your standard vortex impeller. So let's compare progressing cavity pumps and centrifugal pumps just a little bit more. So progressing cavity pumps can produce very high pressures, but very low flows. Typically, on average, you're going to see about 11 gallons per minute from these pumps. However, they can handle pressures up to about 240 feet of head. At least with our 2 horsepower model, that's what you'll get out of that pump. On the other hand, you have centrifugal pumps. These pumps produce higher flows compared to progressing cavity models, but output lower pressure. So typically you're going to see between 35 to 55 GPM with our 1 and 2 horsepower centrifugal pumps. And the shutoff head is around 100 to 125 feet. So not as much pressure, but definitely much higher flows. So with progressing cavity pumps, they're great for residential applications, specifically in low pressure sewer systems, since they can produce such high pressures. And typically residential applications, residential homes don't really need a whole lot of flow out of their pumps. Now, because of this, they're not great in commercial applications. And that's because with commercial applications, you tend to need higher flow rates out of your pumps. And since you're not getting very high flow rate out of that progressing cavity pump, there can be issues where the pump is not keeping up with those flows coming into its enclosure. On the other hand, we have centrifugal pumps, and these pumps are great for both residential and commercial applications. They have very high flow rates, and can handle those flow rates that you're going to see coming out of those commercial applications much better than a progressing cavity model can. Another thing about progressing cavity pumps is that they only rotate at about 1750 RPM, whereas centrifugal pumps have a 3450 RPM motor. What that means is that a progressing cavity pump's cutting capability is not nearly as good as a centrifugal pump's cutting mechanism. And that's just because since that cutter is going to be rotating much faster in a centrifugal pump, that cutting action and the size of those solids are going to be much smaller, and that cutting action is going to be better than that progressing cavity pump. Another thing about progressing cavity pumps is that they offer very limited scouring for pipe networks. So for those that don't know what scouring is, sewage applications, you have to maintain a limited velocity or a minimum velocity to keep sewage suspended at all times throughout that pipe network. So 2 feet per second is the minimum for most sewage applications. And that's what scouring is. Scouring velocity is going to be that 2 feet per second or more throughout a pipe network. Since centrifugal pumps can put out a whole lot more flow, these pumps typically have better scouring capabilities than your progressing cavity pump. However, the main weakness of a progressing cavity pump is also its main strength, which is its rotor and stator design. Because there's added friction inside of a progressing cavity pump when compared to a centrifugal pump, typically progressing cavity pumps don't last as long as centrifugals. Whereas with centrifugals, they don't have as much head capacity as a progressing cavity model. So now let's talk about radial and axial cutters on grinder pumps. So radial cutters are the old style of cutting. This cutting mechanism rotates inside of a stationary shredding ring. They are in the same plane, and I'll show you that here in a second. But that shredding ring has teeth on the inside diameter of that pump. The problem with this design is that there's these grooves between the rotating mechanism and that stationary shredding ring. And those grooves can start to fill with debris the longer that they're inside of an application. So this can lead to reduced flow into that pump and eventually can clog that pump. On the other hand, we have axial cutters. And these are designed to handle today's solids content. These are the newer style of cutting mechanism. So this comes with a cutter and a cutter plate, and that cutter is positioned on top of that cutter plate in very tight tolerances. So what this creates is a scissor-like cutting to grind up all of those solids, which leads to a lower chance of anything clogging that cutter and cutter plate. Another thing to note is that with this design, typically there are curved edges on that cutter, which will push away those larger solids from the inlet when that pump turns off. So if that pump is in the middle of grinding something up, those curved edges can help push away those solids and prevent a clog from happening when that pump starts up again. So here I have two different images, one a radial cutter and one being an axial cutter. So that radial cutter there, you can see the cutter in the middle of that cutter plate. That cutter plate is that outer ring. And in between the two, which is what's highlighted here, that's typically where debris can start to clog up that cutter and cause problems. Whereas with the axial cutting mechanism, this is not really a problem. You're not going to really deal with a whole lot of debris building up inside of the cutting mechanism in that cutter plate. So now let's move on to cast iron and oil inside of our pumps. So the number one killer of pumps is heat. So nearly all Zoller pumps utilize cast iron housings and oil-filled motors to dissipate that heat from the motor to the surrounding water. So the dielectric oil inside of that motor housing better transmit heat to that pressed motor housing. And because that motor housing is made of cast iron, that cast iron dissipates that heat to the surrounding water. And this is typically better than other materials that you may find with pump builds. So another thing to note is that we have finned housings on our housings or on our pumps. And this helps increase convection, which is just increasing the amount of heat that is transferred between that pump to the surrounding water. The more contact that you have with the surrounding water, the better that heat is going to transmit out. So continuing on, let's talk about oil versus air-filled motors. You may have heard of air-filled motors before, and we have decided that oil-filled motors are better. And here's the reasons why. Oil-filled motors tend to run cooler than air-filled motors, and that's because oil is just better at transmitting heat than air is. That's why oil is used in a lot of different mechanical devices. Another thing is reduced wear. So oil is a lubricant, and because of that, the components inside of that pump remain lubricated from that oil, which can help increase longevity of that pump. Whereas with air-filled motors, these tend to run hotter inside the pump, and also this leads to increased wear of those pump materials. Since you don't have that oil lubricating those materials inside of that pump, those components are going to fail much faster. Now, one thing to note is that you will see that air-filled motors tend to be a little bit more efficient than oil-filled motors. However, this is only really at the beginning of that pump's lifespan. As that pump is operating, those air-filled motors are going to reduce in efficiency over time, and that's because of that increased wear on those internal components. Whereas with oil-filled motors, that lubricant helps prevent wear and lead to longer life and more steady efficiency throughout its life. So now let's talk about mechanical seals. So a mechanical seal is a rotating and stationary ring that are compressed together by a spring. So one thing to note is that rotating face ring is sealed to the shaft, so it rotates with that motor, and then that stationary ring is sealed to the housing of that pump. The whole reason for using a mechanical seal is we want to keep oil inside of that motor and keep water out, since water will cause a failure of that motor. So first, let's discuss various shaft seal materials. Really, we're going to discuss carbon ceramic versus silicon carbide, which are two very common materials used in shaft seals in the pump industry. So carbon ceramic seals are going to be your standard seal. They're used in most water applications. They're very cost effective, and they have good thermal shock resistance, which just means that if there is a spike in temperature, that carbon ceramic seal is not going to start to break down. Now, if there's a constant high temperature, that's a different story. We'll get into that here in just a second. But these seals are going to wear faster compared to silicon carbide, since silicon carbide is just a better material, and they tend to be a little bit less durable than a silicon carbide seal. Now, that doesn't mean that a carbon ceramic seal is not a good seal. There's a reason why it's used in most water applications. However, you want to consider using a silicon carbide seal in applications where your pump is going to be running more often than not, or if you're going to have chemicals or gritty material that's going to be inside of that pump or inside of that wastewater, because that can start to break down a seal that isn't meant for that type of application. So a silicon carbide seal is going to be much better and last much longer in those types of applications. The thing to note is that silicon carbide seals, because it's a better material, tend to be a little bit more expensive than carbon ceramic. However, they're very wear resistant and they have a longer lifespan than a carbon ceramic seal. So let's talk about single seals versus tandem seals. So a single seal pump typically has one seal between that impeller and that the housing section where water is going to be moving through that pump and the motor. The problem with that is if that seal fails, then water is going to come in and it's going to cause a premature failure. So in more demanding applications, we tend to recommend upgrading to a tandem seal pump. A single seal isn't necessarily needed in smaller residential applications, but when you're getting into the more industrial and commercialized applications, tandem seal pumps tend to fare better. A tandem seal pump has two seals rather than one. So there's one seal between the impeller and an additional space inside of that pump where if that seal fails, water will fill up that section before reaching that second seal, which is between that additional section and the motor housing. And I have a cutaway to show you here in just a second. The main advantage of this is that if that first seal does fail, then you have warning that there is a seal failure and you can get that pump serviced without having to replace that pump entirely. So the easiest way to tell the difference is usually tandem seal pumps have an additional section on that housing. So if you compare that single seal and tandem seal, you'll see that that pump's a little bit taller and there's that additional section where those moisture probes are going to be located. So here's that cutaway that I talked about. So right here, that is where the seals are going to be located. You can see that bottom seal between that impeller and the first section of that housing. So if that seal does fail, water will fill up, and that moisture probe, which is that rod on the right, will detect that there is a seal failure and notify you. Now, another thing is that with tandem seal pumps, these are two completely separate seals. There's nothing that is really connecting the two seals. So that means that that second seal between the housing and that additional chamber is really been operating in ideal conditions. There hasn't been any water inside of that chamber, and that means that that seal's lifespan is much longer than that bottom seal, which means that if that bottom seal does fail, you don't have to worry too much about that second seal failing around the same time. So here's a good little cutaway of that tandem seal. These are two seals that are oriented in the same direction. That's primarily what we use on our dual seal pumps. As you can see, they're completely isolated. There's nothing really connecting the two other than the shaft. Now, you may have heard of a double seal pump, and you might have heard these two terms used interchangeably, but there is a major difference between the two. A double seal pump are two seals that are oriented in the opposite direction. What that means is that these seals use one spring between the two. So if that spring ever does fail, then both seals are going to end up failing. So it's good to keep an eye out for what type of pump you're purchasing for your application. A double seal pump tends to be a little bit cheaper than a tandem seal pump. However, you are losing some of that redundancy with that double seal pump sharing a spring between the two seals. So that's just something to keep in mind. Like I said before, we use tandem seals on our pumps to ensure the longest life out of those pumps. So now let's talk about power. This is where we're going to get into more of the application-based side of this presentation. So first, let's discuss supply voltage. So what's in the name, your supply voltage is the voltage supplied by the utility company. And these typically come in variations of 120 volt, 208 volt, 240 volt, 480 volt, and 600 volt, like what is shown on that chart below. Then you have the nameplate voltage. That is the voltage that a motor is rated for. And this tends to be a little bit lower than your supply voltage. And this is really to account for voltage drop between that supply voltage and the pump itself. So the nameplate voltage comes in 115 volt, 200 volt, 230, 460, and 575 volt. So let's talk about these differences a little bit more. So utility companies are required to supply voltage at a plus or minus 5% of the standard supply voltages that we just saw on the previous slide. So to account for this variation in power supplied, NEMA, which is the National Electric Manufacturers Association, recommends that motors operate at plus or minus 10% of those supply voltages. And that's really to ensure that that pump is going to operate no matter what supply voltage is supplied by that utility. However, it's important to know that you want that motor and that supply voltage to be as close together as possible. And that's because the closer you are, the longer life you're going to get out of that pump. So another thing to note is I talked about voltage drop before, and this is related to impedance, which is your resistance in electrical wire. This is very similar to to your frictional losses in a pipe network. The smaller diameter cord and longer length you have equals higher impedance, which means a higher voltage drop, which is why pump manufacturers tend to limit how long of a cord you can put on pumps so that we can limit the amount of voltage drop that can occur between net supply voltage and the pump. And just the same as with pipe, the larger diameter cord and the shorter length you have equals lower impedance, which is lower voltage drop. So now let's get into hazardous environment applications. So let's talk about intrinsically safe first. You might have heard of this before. Intrinsically safe devices are designed to limit the electrical energy available for possible ignition, and this falls under the NEMA 4X classification. So typically you're going to see intrinsically safe panels and low current float switches, and these fall under this intrinsically safe this intrinsically safe designation. So with intrinsically safe panels, you're typically going to have intrinsically safe relays like what is shown on your screen here. And then you're also going to have intrinsically safe barriers. And that's just to separate those higher voltage components inside of that panel from the lower voltage components that are going to connect to your pump station. Another thing is you're typically going to use low current float switches to reduce the amount of amps that are going to be inside of that pump station and to reduce the possibility of an ignition. Now, one thing to note is high power circuits cannot be intrinsically safe, which is why you don't see intrinsically safe pumps. Instead, you're going to see explosion-proof pumps. These are designed to contain an internal explosion and prevent igniting the surrounding environment. This falls under the NEMA 7 classification. So this is going to be used in hazardous environments where high power is needed, which you need high power to operate a pump. Now, one thing to note is it is very expensive to make all components and assemblies explosion-proof, which is why you don't see a whole lot of explosion-proof panels. They do exist, but for most applications, you don't really need an explosion-proof panel. And because of that, it's going to be significantly more expensive than just an intrinsically safe panel. So that's just something to keep in mind. So let's talk about the two different classes that our explosion-proof pumps are rated for. So Class 1 Division 1 means that there are going to be flammable gases, vapors, and liquids inside of that hazardous environment. Typically, you're going to see this designation for refineries, dry cleaning plants, chemical manufacturers, and any other manufacturing plant that's similar to these. Now, our heavy-duty sewage pumps like the 61, 62, and 64 HD, as well as our grinder pumps, the 7011, 7013, 71, and 72 HD, fall under this Class 1 Division 1 rating. Our commercial duty pumps also have variations to fall under this rating as well, being the 6160, 6180, and 6290. And then on the other hand, we have Class 2 Division 1, which means that there are going to be combustible dusts inside of that application. Typically, that's going to be sawmills, metal powder manufacturers, and coal plants. Our commercial duty pumps, the 6160, 6180, and 6290, are also available in an explosion-proof variation. So now let's talk about operation, specifically continuous and intermittent operation. So this is generally what people mean when discussing continuous versus intermittent operation with pumps. So an intermittent operating pump is going to start and stop periodically, and this is going to be most of your pump applications. However, continuous operation is exactly how it sounds. That pump is going to run nonstop. If you want a pump to operate correctly in a continuous operation environment, you're going to want to make sure that pump has some critical upgrades and are rated to withstand that added wear and tear from continuous operation. So now let's talk about continuous and intermittent duty. Sometimes people tend to use these interchangeably, but there is a major difference. So continuous or the duty rating is tied to the thermal characteristics and requirements of the motor. Most motors have stators that have insulated wire that can break down at high temps. And that's just because electrical current will arc between uninsulated wire, which can cause hot spots and cause premature failure. So you want to make sure that if you are putting a pump into a continuous operating environment, that pump is rated for continuous duty. Continuous duty means that pump can operate indefinitely without exceeding the motor's thermal limits, whereas intermittent duty cycles are the length of time a pump can run before resting back to ambient temperature. Most pumps have intermittent duty ratings versus continuous duty ratings. However, some pumps, like quite a few of our heavy duty pumps, can be put into a continuous duty environment up to a certain water temperature. So be on the lookout for that. All pumps can be put into a continuous operating environment, but that does not mean that they are going to last for a very long time. So if you are going to have a pump in a continuous operating environment, it's good to have that continuous duty rating to ensure that pump is going to last as long as possible. So now let's talk about wet well and dry pit applications. So wet well applications is going to be your typical installation of submersible pumps. They're going to be in some kind of pump enclosure, like a basin, and there's not going to be any inlet piping that's going to be attached to that pump. Now, the main considerations that you need to make with wet well applications is going to be your head and flow, as well as if there's any sort of high temps or abrasive material that might be found in that application. With dry pit applications, there's a few more considerations. So with a dry pit application, that pump is going to be installed outside of the wet well, and you're typically going to have some kind of suction pipe at the inlet of that pump. Now, one thing that you really want to keep in mind and avoid is going to be cavitation, which is a consideration when you are making a pump selection for a dry pit application. So just to show you the two differences, the wet well application is most of your standard pump applications, which is shown on the left. Those pumps are typically going to be inside of a basin and maybe on a rail system. And as you can see, there's no real pipe connecting to the inlet of that pump. Whereas with a dry pit application, you're going to typically have some sort of adapter or just pipe that's attached to the inlet of that pump, where that pump is going to be sucking water through that pipe into the pump and then out the discharge. So now let's talk about cavitation. So why are we talking about wet well versus dry pit? So cavitation is the repeated collapse of vapor bubbles. This can occur when the pressure in the water drops below your vapor pressure. The reason why cavitation is such a concern in dry pit applications is because this can start to erode your pump components, specifically your impeller. That can cause heavy damage to the impeller. It can reduce the efficiency of the pump, and also cause excessive noise and vibrations. And like I said before, this typically occurs at the center of that impeller, which is where you're going to see most of the damage done by cavitation. So if you want to prevent cavitation, in wet well applications, submersible pumps are already tested for these types of applications. You really just need to stay on that pump curve to prevent cavitation from occurring. Now with dry pit applications, this is where cavitation can become an issue. So NPSH stands for net positive suction head, and there's really two different variations. You have your net positive suction head available, which is going to be your net positive suction head that occurs in the application, and then you have your net positive suction head required, which is the required NPSH for that specific pump model. So whenever you are designing for a dry pit application, you want to make sure that NPSH available is higher than your net positive suction head required. If that available NPSH drops below your required NPSH, that's when you start to see cavitation issues. To ensure that your NPSH-A is higher, you want to make sure that you have properly designed suction piping. You want to make sure that there's no places inside of that suction piping where air can get trapped and cause that NPSH to drop. Another thing is that you want very minimal elevation difference between the water location and that pump. Typically when that pump turns on, the water is going to be sucked through that inlet pipe. So you want to make sure that there's not a whole lot of elevation difference between the two. That's going to limit, or that's really going to help prevent that NPSH dropping below your required NPSH. Air entrainment is another issue that we see in pump stations, and this is in both wet well and dry pit applications. So the reason why we're talking about it is that it has very similar failure modes to cavitation. Typically with air entrainment, you're going to see reduced efficiency, erratic flow, and increased vibration and noise. Air entrainment is just external air that is drawn into the system. Usually this is because of improperly designed intake piping or the water in the wet well not being high enough to prevent any sort of air getting drawn into that pump. So in wet well applications, you want to make sure that there's proper submergence. You can also use air release valves, and typically all of our pumps have weep holes to release any sort of air that might get trapped inside of that pump. But you also want to make sure that you're putting weep holes into that discharge piping to get rid of any of that air if that first weep hole does become clogged. And then we have dry pit applications. Like I said before, you want to make sure you have properly designed intake piping. And you can also use air release valves and weep holes as well to prevent any sort of air from getting trapped in that system. So now we're getting on to our final topic, which is going to be variable frequency drives. So typical power distribution in the US alternates at a frequency of 60 cycles per second or 60 hertz. Motor speed and RPM is directly related to said frequency. We typically design our motor speeds to go at 60 hertz within the US. So by varying that frequency, you can change the speed of that motor. And there are many reasons why you would want to do something like this. But first, this is typically what a VFD curve is going to look like. That 60 hertz curve is the standard curve for whatever pump you're putting in, and then the curves below that curve, so the 55 hertz, 50 hertz, and so on, is going to be the new operating points for that pump when you start to vary the frequency going to that motor. So as you can see, as you decrease that frequency, your flow and pressure capabilities of that pump are also going to decrease. So there are a lot of advantages to using VFDs. One is tailored flow on demand. So you can alternate however much flow you're getting out of said pump to fit the current conditions of your application. Another thing is reduced pump wear. Typically when you're lowering the frequency, that pump is going to start fewer times since it's not putting out as much flow. Another thing is you can hit varying design parameters using a VFD. This is fantastic for stormwater applications where you may want a pump that can handle, say, a 100-year storm, but you also want to be able to drop that pump's operating flow downward towards more of a 10-year storm during normal conditions. So then that way you have one pump fulfilling two roles in that application. Another thing is VFDs help to reduce energy consumption by pumps. You can also use VFDs for soft starting. So what that means is you start the pump at a lower frequency and then ramp it up to its 60 hertz frequency. This is great for reducing the amount of amps that pump is drawing at the beginning, which can lead to longer life. However, caution needs to be had with sewage ejectors, specifically so that you are meeting those minimum scouring velocities going through that pipe, so you don't have any clogs throughout your system. And then lastly, you can use VFDs for phase conversion as well, typically from single phase to three phase. So this is great when you only have single phase power, but you need the power and capabilities of a three phase pump. So you can use a VFD to convert from single to three phase. So typically, if you're going to be using a VFD, you're going to want an inverter duty rated motor. So this just means that is an upgraded motor from the standard motor that pump would come with. Comes with a Class F insulation for that wire, and it's also wounded with shielded wire as well. The reason for that is VFDs can start to create hotspots on standard motors, which can cause a premature failure inside of that pump, which you can see that here on the right. So also with inverter duty motors, you're going to get Viton elastomers and silicone carbide shaft seals. And that's really just to further increase the life of that pump. Now, one thing to note is that with inverter duty motors, this is not, you don't really need them for soft starting or phase conversion. So you only really need inverter duty motors when you are actually varying the frequencies frequently. Next up is we're going to talk about bearings with VFDs. So fluting is a common bearing failure in VFD applications, and that can be shown on the right here. You can see that the shaft currents from those VFDs has ground through that motor bearings and caused a premature failure. That's what those grooves are in the side of that bearing. Now, the way we combat this is providing what is called cool blue inductive absorbers, which you can put around that pump wire. That's going to prevent bearing fluting, and it's also going to lower the operating temperatures of that pump, which is also going to contribute to longer life out of that pump. Okay, so this concludes the presentation portion of our webinar. We've uploaded some handouts regarding the information presented here today. They include various technical writing documents that expand upon some of the subjects that we've discussed here. So be sure to download that if you want future references for what was discussed here today. Should you think you might have lingering questions, again, please send them our way through our webinars email, webinars@zoller.com. And with that, we'll wrap things up. Thank you all so much for taking the time to join us today. Have a great rest of your day.